So hello everybody, my name is Heikki Kortti. I'm here talking to you today about something that's related to the previous talk we saw on fuzzing. I work at a company that does fuzzers for various network protocols and file formats, including also wireless stuff. So I found the previous talk in this room very interesting from a professional standpoint. I have to, in the beginning, say a few practical things. If you have any questions, it's okay to interrupt me at any time. I'm a nice guy, so I won't shoot you if you shout obscenities from the audience or curse at me for saying some improper things. It's also okay to stay here or go outside after the end to discuss some matters if you want to discuss some things privately with me. There's also a nice page in the wiki for DeepSec for each of the talks. So if you have any questions or ideas that come to your mind during the presentation, criticism, comments, questions, feel free to go in and even edit the wiki page for my presentation and add your questions or comments there. I'd like that. So without further ado, I'll start discussing some of the topics that I have on the agenda today. So we've seen a lot of talks about vulnerabilities, about ways to exploit flaws in software, but my talk concentrates on a more specifically input-oriented approach. So I'll be just focusing mostly on how to design effective inputs that traverse a software system and make trigger bugs or vulnerabilities in the system. I won't be talking about ways to do advanced exploitation or take advantage of the flaws that are found. I'll more be talking about what kind of inputs we can create that trigger the vulnerabilities that might reside in any software. So we've coined the term destructive data as this kind of fancy word for designing inputs that make software fail in various unexpected ways. I like to think of this as kind of like cathartic testing. So if you know the Greek term catharsis, it's a mindset where you think that through destruction you actually can improve things. So it's kind of constructive destruction if you allow a paradox. So when we are discussing destructive data and ways to design destructive data, you must really think like you were a malicious input going through a system, traversing all of the various components in a system, going through the parsing stages, all the way up to output generation stage. You always have to think specifically about the interface that you are approaching. So if you are trying to break a network protocol, it's a little bit different from breaking a file format implementation. So you must always still think how your inputs that you are creating will actually go through the software and what kind of effects, what kind of code it might be passing along the way. So typically the inputs that we create, they are captured by a parser maybe. The parser passes it on to deeper layers. The data is transformed, it's processed in various ways, and finally it reaches some inner location in the code. You should always also think about what kind of possibly underlying flaws are there in the code. So you might think of buffer overflow conditions, but you might also think of state machine problems, null pointers, what have you. So you should always consider if you make a different kind of input, what kind of flaws it can actually trigger. The most important thing when designing destructive data is to really think malicious. I'm sure this is no problem for many of you, but some people think of still approaching software and testing software as performing some kind of valid interactions with the software. But the main thing is to forget all about that and start thinking really in a malicious way. Start doing everything that is not expected by the software, breaking its assumptions in all levels, so to speak. So if you are looking at the network protocol, for instance, if there are type fields, length fields, different kind of values, header versus payload situations, or there are state machines defined in the protocol specification, even things like how is logging done, how is debugging done for a particular input, those are always very important aspects to consider when testing something. So you might think of what are the effects of parsing a particular length field, what kind of interactions will the software do after it has read in a particular length value from an incoming message, or if you can somehow tweak the header versus the payload, so make the header look like there would be something else expected in the payload, and so on. So you should consider all of these different kind of sort of basic primary elements in protocols and file formats. Most of the time it helps to know really if your target that you are attacking, whether it's written in C or C++, that's kind of an obvious thing. But it's not always strictly necessary. You can also start creating malicious inputs and then later on find out what are the conditions that are being triggered. So actually when designing the malicious inputs and when injecting them into your target system, you might accidentally find out that the target is written in a particular language because of the types of vulnerabilities that you are unveiling. So you might approach, if you know the internals of the system that you are testing, that always helps. But you can also approach the tested implementation as a completely black box without any prior knowledge, except from the fact that it has a particular interface that you can use to start injecting your tests to. Now, a couple of terminology issues. When we think of destructive data, the primary term that we like to use is called anomaly. We think it's a good term because it captures kind of the idea behind what we are doing. So it's destructive data is a good sort of fancy word, but anomaly is more, it captures the idea of what we are doing. It's basically any kind of malformed input. It doesn't have to be just some kind of fuzzed value field. It can be like really unexpected things like reordering a sequence of messages, for instance. If you think of a complex protocol message sequence like TLS or BGP, for instance, you might reorder the messages in that, reorder the expected order of messages in that message sequence. So you might start finding really interesting things just doing this kind of very simple approach. Or do things like cut a file or a message abruptly in the middle. You make a valid file or valid message, and then you suddenly cut it from a location somewhere within. Or doing things like deep recursion for a file format that allows that. So it doesn't have to be that you are fuzzing a single field or single element. You should think of anomalies in a wider way. You should always think of sequences as well, sort of substructures that you can also undermine, and think of also combining things, not just anomalizing one field, but anomalizing multiple things in a message at the same time, sort of going crazy with anything you have at your disposal. Now, when we talk about the destructive data and anomalies, the inputs that you use to attack software, vulnerability is the underlying condition. It's the bug, it's the flaw, programming error, or some vendors call it just issue, that the destructive data is actually able to trigger. The anomalies that we create and send to a piece of software, those trigger the underlying programming errors that may exist in the software. Symptoms can vary a lot, as I'm sure you've all seen in your practical work. We might see crashes, we might see exploitable conditions. You might be able to exploit a particular, let's say a buffer overflow or a similar kind of issue. But you might also see temporary slowdowns of the system that you are testing. You might see things like memory, CPU consumption, resource problems, errors in actually log file handling, for instance, things like portions of the log files disappearing as a result of the data that you are sending. Also, what's called like second-order vulnerabilities, meaning that this data that you send ends up in another location, like let's say SQL backend, and when somebody is using a log analysis program, it might actually trigger some within that log analysis program. So sometimes the symptoms are very surprising. Like I have to say that I'm always surprised by the different kind of symptoms that very simple malicious data can cause in software. So we've seen some very amazing things happen in some devices, as I'm sure you have seen during your career or work. So a lot of the time the underlying errors are the simple vulnerabilities that we have heard about in most other presentations or through your own research. Basic buffer overflows, pointer arithmetic problems, different kind of type conversion issues, memory management problems, memory allocations, or not freeing elements that have been reserved. Some kind of input sanitization problems. There might be no filtering done for incoming data, no sort of sanity checking for the inputs that are coming in. Or if there is some debugging information output to the log files, there might be a problem with sanitizing the destructive data that is actually then moved to all the way to the log. So input sanitization, yes, but also output sanitization. You don't want your log files getting filled up with ANSI escape sequences, for instance. So then when we discuss exploitation, it's yet another view of the same sort of problem. So destructive data looks at ways to trigger vulnerabilities, but exploitation is then another way of taking advantage of the vulnerabilities that are found. So I'm actually in this presentation not discussing the vulnerabilities and the exploitation of vulnerabilities in any practical detail. I'll actually be connecting some of the anomaly categories that we'll see to some representative programming flaws and giving you a couple of case examples of what kind of real-life errors can be found with very simple destructive data. So there's two basic ways of looking into the same underlying condition. You might think of the situation from the point of view of the destructive data, from the point of view of the inputs themselves, or you can concentrate on the underlying flaws. Many times if you have a solid programming background, you might more consider about the vulnerabilities and ways to exploit them. But if you think of the view from a black box testing standpoint, it's more concerned with how you can actually trigger the flaws. You don't care about the flaws themselves that much. You care about the ability to create representative inputs that will trigger certain categories of flaws. So the basic problem is really like when you are designing anomalies and designing these kind of fuzzing tests, what are the flaws that typically can be reached by particular kinds of inputs? So you might create some very advanced and fancy attacks, but you might not always know what kind of programming error is being triggered by these attacks. There's really an easy solution to this. You can connect your anomaly definitions and ideas about the ways to create destructive data with common categories of vulnerabilities. And that's a rather simple insight, but it goes a long way into actually documenting what you are doing with your destructive data and connecting it, possibly providing some information to the developers, providing some information to third parties about what are the errors that you are actually triggering. There's a thesis work from a colleague of mine who is actually focusing on just this ability to connect the destructive data with or assess the quality of destructive data by connecting it to the different types of vulnerabilities that it can trigger. One system that I'm sure you all are familiar with already is the common weakness enumeration effort organized by Maitri. CWE is a way of enumerating the common programming errors, common vulnerabilities, common weaknesses in different programming languages. There are some things there that are programming language independent and some issues that are specific to Java, C, C++, so on. So it's a listing, it's a database of different kind of weaknesses that plague modern software. So just as an example, we might think of example piece of destructive data, a repetition of one single ASCII character 256 times. Very simple kind of attack that can trigger a common programming error. And typically this kind of attack might trigger is a basic stack-based buffer overflow, for instance. There is a CWE ID for this kind of condition, so you might think of the destructive data first and then see how it maps into the underlying vulnerabilities. So it's a good way to describe what you are doing in a language that's also understood by the people who program the system, the people who have developed the system, or by trusted third parties, by search, for instance. If you are finding a vulnerability with a particular type of attack or malicious input, you can then use the CWE information maybe to give some initial information on what is possibly the underlying problem, even if you would not have access to the source code of the system that you are testing. There's a caveat here that CWE is still very much a work in progress. There's a lot of work being done by some of the MITRE guys in standardizing and actually collecting information on the different types of weaknesses that are out there. So in case anybody has some free time or too much free time in their disposal, like I would suggest that you take a look at CWE, and if there's something's missing there, you can help the MITRE guys improve it. Okay, so moving to discuss the different kind of expectations that software has about data. So I'm sure you're all familiar with the abbreviation TLV, type length value, which basically forms the underlying structures for any kind of protocols or file formats. So I'll go through some of our ideas about these different basic data types and take a look at what kind of attacks can actually be implemented or constructed against fields of these types. So let's take a look at some of the basic types. So the type fields in a protocol or file format, they typically define what kind of things are expected later on as, let's say, values or payloads or whatnot. So the type can be explicit. So there might be a protocol specification that says that there is a single type field with well-defined values that tell what kind of value is expected later on in the message. That is an example of an explicit type field. So when you know that there is an explicit type field, you can just start attacking it right away. Just change the type into something different. It's as simple as that. You already then undermine the expectations of the software that you are attacking. It's expecting for a value that is completely different. The structure for the value that comes later might be completely different from the one that the software is expecting. So usually these kind of types and their expected values are usually defined in some kind of specification. If it's a public, whether it's a public specification or a proprietary specification, there is always still some kind of mapping between the type fields, explicit type fields, and the values that are accompanying them. So you might also have implicit types. So you might have a header field in a, let's say, ASCII protocol where the value for that particular header field is expected to be a URI. It might be referenced in the specification. There might be some kind of implication that a URI is expected, for instance. So this kind of type information can also be implicit in that sense. So you should always then try to mismatch your types and values. You should always try to tweak the types, use types that are not defined in the specification. Length fields, that's probably the most fruitful way of attacking modern software. Whenever there's a length field, there is a problem in handling those lengths and the values that those lengths define. So a length field simply defines how long or where a particular data section or a value is located, or how long the value is. There can be varying flavors of lengths. You might have very kind of explicit basic length fields saying that, well, here's a length, and after that will come a structure which is supposed to be of the specified length. But also things like element counts, offset values, array indices, length delimiters, they can also be thought of as length fields. An explicit length field is by definition something that you find existing within a protocol message or within a file format. So it's something that has been defined to be there. But there's also implicit lengths. So for instance, DNS name elements should not be more than 32 characters. IPv4 address is typically assumed to consist of 4 octets, and so on. So there might be these kind of implicit length constraints on the values that come later. And you should always try to undermine the length expectations both for explicit fields and also for implicit things. So if there is a space for an IPv4 address, why not make it like 1 octet and see what happens? Why not omit it completely and see what happens? So these kind of implicit lengths sometimes are very destructive in themselves, because there is some kind of expectation for the software that the data that comes in should adhere to a particular format. Especially if you have like multiple length payload dependencies. The best known example probably is the length fields, different length and offset fields in IPv4 packets. That's a very highly problematic thing to implement. So whenever you have payloads that overlap each other with length fields on each layer, it's always very fruitful ground for actually attacking and tweaking the lengths at all levels. So these length and offset fields, they come in multiple forms. You might have different types of endiannesses or lengths of the length fields themselves. You might have variable length, which is an insane idea. So ASN1 being the canonical example of these kind of weird things. Whenever you know that there is a length specified somewhere, you should obviously try very large lengths. Try very small lengths. Break the dependency between what is in the value and what is specified in the length. So you can try for things like very large length but a very small value, or you can try very small length and a large value, those kind of things. And it's always a good idea if the specification says you can try 0 length, or even if the specification doesn't say that, why not try specifying a 0 length and see what happens, or negative length if that's allowed. Especially if the length is specified as some sort of string, it's always good to try -1 and see what happens. And if you have this kind of multiple overlapping length fields, just like go crazy, break all of them at the same time, try anything. Now, a lot of ASCII protocols they use delimiters quite heavily, and they are kind of like length fields in disguise because they specify limits to the data that can be transmitted. So ASCII protocols might have various kind of delimiters, and sometimes they use multiple different delimiters in confusing contexts. There might be new line spaces, commas, colons, forward slashes, backslashes, and so on. End of lines, null characters, zero terminated strings, these kind of things. They're all delimiters which state where the data should end or where it should start in another view. Some binary protocols also use length delimiters. ASN1, which is a bad idea in general terms, it's using this kind of indefinite length delimiter. You might have a single field or structure that has multiple different delimiters. So let's say URIs, for instance, they have various kind of special characters that can be considered delimiters, and you can always try to break them. So whenever you know that there is a delimiter specified, if you are trying to break a public protocol, for instance, or if you know that the proprietary format has certain kind of delimiter looking fields, you can always try to omit delimiters. You can try to overflow the delimiters themselves. So why not, in the case of like, let's say URI, why not insert like 10,000 colon characters at the end of the URI method, or do any kind of things. The other thing would be to try also wrong delimiters. So try, let's say, different kind of, try a semicolon instead of a full colon, or do any kind of weird things that you think might confuse the parser who is trying to make sense of the delimited pieces of data. Now, if there is a length field and a delimiter specified, that usually leads to catastrophic failure right away. So the belt and suspenders approach of using a length field, explicit length field, and then using delimiters in the actual value, very canonical example being length field and null terminated strings. That opens up again a new can of worms. You can then again try to omit the delimiter, use a delimiter in the middle, try it in the beginning, use multiple delimiters within, let's say, a string, use nothing but the delimiters, what happens then when there is no actual value, or you can then start tweaking the length field and then do all kinds of other things with the delimiters as well. Now, having looked at the type and length, when it comes to value, it's kind of the data that comes after the type and length, either explicit or implicit fields. Data is kind of ephemeral thing because many times the value itself is TLV again. So the value itself has some kind of either explicit or implicit substructure that can be looked at as another level of structural data. So the many values, actually most values, they have some kind of expectations for the validity of data inside the value. When you are attacking a basic value field, just try using a huge value, like very long value, or use very tiny value field. Compress everything and just use like one byte, or even 1 bit. You might run into some bit alignment errors or various other conditions if you just cut the value very short in the beginning. Always try different boundary lengths. For most values, there is some kind of buffer or boundary specified where the data gets stored. So try the different kind of boundaries that you could expect the underlying software to have. If there is some mandatory value specified in a protocol, for instance, or a file format, you should always try to take it away. Just don't let the software have its candy. Take it away from it and take away the value that is expected, that is specified as mandatory in a specification. That usually confuses a lot of systems. And then if you know that there is substructure within the value field, you should always start breaking it as heavily as possible. Look at the value as another TLV tuple, and then start breaking the type, length, and value within that substructure. So look at the value as another level of constructing malicious data. So for values, the most canonical example and the classic example obviously is the classic buffer overflow value attack. So nowadays buffer overflows can mean like other things as well. So the term has undergone some inflation within the past years. But traditionally the buffer overflow used to mean a very simplistic kind of fitting a particular piece of data into a fixed length buffer. And the way to attack this kind of basic buffer overflow is obviously to just increase the value, make it very big, make it bigger than the buffer that would be reserved for it. Try different kind of boundary values again. Usually it's okay to try -1 to +1 around each boundary. So those typically catch a majority of the errors. One important thing is that when you are making a buffer overflow, why not try also something else than the canonical ASCII attack. So you should actually, sometimes we've actually seen programmers do filtering mechanisms that filter long strings of A's from inputs, for instance. So the best example was when there was a buffer overflow reported to a vendor, and they actually looked at the data that was sent in the POC to them, and they looked at, well, my software has a problem with handling 150 A characters in the input. So they put in a filter that said, if there is 150 A characters coming in, discard the input. And they said, well, now the software is fixed. So when the patch came out and when there was another attempt to break it, we found out that, well, 151 A's caused the same problem to appear again. So try different characters than the canonical overflow attempts. Try numbers, try control characters, for instance. Do some crazy things. You might actually find some of the crazy things that the programmers themselves have done. A lot of the time the values themselves, like I said earlier, have some kind of substructure. So let's take an example, like there might be a value that's specified as year, for instance, or actually month inside the year. It can be year as well. But let's say that there's a value field that says that this is the month number within a year. So why not try something else at that location and see whether there can be a 13th month in your year. Or there can be expectations if there's a person's age somewhere handled in the application. There's an implicit assumption that nobody should be over a particular 200 years or something. Or that if you are handling dates, nobody cares about dates before like 1800 or 1900. So why not try something like 0 as the year and see what happens, or -1 for that matter. Or that if there is a name field in an application, let's say a web application, for instance, somebody's first name can't be %s. Why not actually change your name to %s and try to go through airport security and see how the biometric or the computerized scanners actually do with your first name. I'd love to actually try that, but I think most jurisdictions don't allow you to change your name to %s, which is a pity. So often the classification of these kind of implicit value constraints is kind of a gray area. You have to somehow understand what is the implications of a particular data type. Especially with proprietary protocols, it's kind of hard to know if there are some implicit substructure within a value that is expected. So you should always try to then at least guess what are the expectations, or guess what a particular value could be used for, and then start breaking it in every possible way. So another type of value attack is against character constraints. So ASCII protocols typically have a particular set of characters that you should be using. You should not be using certain kind of delimiters within your values. You should not be using ASCII control characters, for instance, in your values. There might also be some constraints in binary protocols. There might be a string field that says that you can only use particular octets within a string. Some examples of basic character sets, this is almost too simple, but Unicode and its various flavors. ASN1 has 10 different string types. SSH is very notorious. It specifies US ASCII for use in internal names, or what's called internal names in SSH lingo. But then Unicode is used for text fields. Terminating null should not normally be stored in the string. What does that mean? Why not try different kind of attacks and see what happens? And if you are trying out these kind of character-based attacks, try converting some malicious attacks, some destructive data into and out of different encodings and see what is the effect. So use a program like Recode, for instance, to experiment with the character sets that your anomalies are using. Compression and escaping, that's another way to sort of attack the values. Sometimes you might try to compress the data so that you can actually later on your data might get expanded and it might later on trigger a particular, let's say, overflow. If you can re-encode the data into a different encoding, or if there's some kind of escaping mechanism, canonical example being like URI escaping, you should always try to use that also to mask your attack into characters that are accepted by the software. So various kind of different encodings, URI base 64, UU encode, just you can try and use anything as long as the system that you are testing is accepting some of them. So these kind of escaped values may pass like initial input validation, so you might be able to sneak a SQL injection attack past a parser that looks into URIs, or do any kind of other things. And then you can also attack the parsing routines themselves. So you can try to kill the parser component that is looking at the escaped sequences. So always escape your inputs, try multiple levels of escaping. So see what happens when you do multiple levels of escaping for a URI, for instance. That means that if there is no checking done after one initial pass of the incoming input, then you might later on reach into some weird routine that can actually will take a look at the escaping and encode it later into a malicious form. Or use try to test also the parsing of escape delimiters. So try sequences of %, for instance, in URIs or various kind of other things. In Unicode you can also try some very interesting things. Here's something I already passed or mentioned in passing. So when we are looking at value fields, it's a nice saying that somebody's value is always somebody else's type length value. So a particular value might be a TLV triplet. It might be just type and value, length and value, or just type for the next level within the protocol or file format. So whether something is really a primitive value versus whether it's an element with some kind of implicit or explicit substructure, it's like a matter of viewpoint. So it depends on what layer you are observing the element from, the value from. So when you are taking a look at layered protocols, simplest example being TCP/IP, you understand the idea behind somebody's value becoming somebody else's type length value. So you should always try to contemplate if there is some kind of inner substructure and try to also reach the next level by breaking the substructure within a value. Another interesting value attack is underflow. So we've seen that some very amazing bugs and problems happen when you start sort of reducing the data that you send, start reducing the value, cut it in half, for instance. Some of the weirdest bugs get triggered by these kind of tests. Typically, the lower layer elements, the value elements, they should somehow fill up the length that is specified for the element, and they should also probably satisfy the expectations for the underlying structures. So make a valid protocol packet, for instance, but then start cutting it from varying locations. Start from 99% at the end. Go towards the beginning of the message until you only have a few bytes from the beginning of the message, or a single byte or a single bit even. So try to cut the packet or file or what have you from various locations and then see what happens. So if you are looking at a single field, make a completely valid message, but start taking away things from that field in various places. But it's very important that the remaining parts in the message or file, they should look still valid for the software. Typically, if you make a completely fast input, it doesn't really make sense, because the system typically will look at it and discard the packet or discard the file right away, because it doesn't look like a valid input at all. But if it otherwise looks as a valid input and suddenly the parser or some other mechanism falls off the end of the packet or field, there's really no telling what will happen. There's a special case, sequence level underflows, which I'll actually go through in a little bit later. Recursion is very fruitful to attack. So the obvious examples being XML, there's an example there. At any point where recursion is possible, it should definitely be attacked without mercy. So you might have some limits, for instance, in a system for the levels of recursion that can take place. So there might be a limit that says you can only recurse like 20 levels. But if you try to reach that level constantly with, let's say, incoming structures, you might still be able to slow down the software and at least find a degradation of service problem. Or if there is a watchdog that is looking at how the software is behaving, if there is a parsing routine that takes a long time to reach the end of the recursion, the watchdog might reset the software. So moving away from the field level anomalization, it becomes really interesting when we start to look at sequences. So not just looking at simple type fields, length fields, or values, but looking at things from a sequence level standpoint. So this is very good technique when you are, let's say, approaching a network protocol that implements a state machine, for instance. So a protocol where you can modify or undermine the expectations of the underlying state machine, it's very good to try different kind of attacks against the state machine. But also parsing components. So a file format that has a particular sequence of structures can also be thought of from a sequence standpoint. So anomaly design is not just about like doing individual value fuzzing, but it's also very important to think about larger structures and their dependencies and the order that they come into the software. Repetition is a great technique, so you can repeat basically anything, and it's easy. It's resource. It's not very resource heavy to repeat a particular thing. If you are doing a fuzzing framework, it's cheap to repeat a lot of things, repeat messages, repeat fields, or any kind of structures. But you can also do it in message sequences. So you can repeatedly send the same message over and over again and see how the state machine, for instance, reacts to repeated structures. Omitting things is just as good. This is the sequence level underflow that I was referring to, or a flavor of it actually. So you might have a definition that says like you have to have a particular message sequence with particular messages or structures coming in at certain points during the sequence. So if you start removing these mandatory or expected elements, you again find some new problems. So you might omit the mandatory field, omit some kind of field that is typically expected in a particular type of message, or omit a message that is absolutely required for a protocol message sequence to go through. Sequence level underflows, this is a special case of omission like I mentioned. So make a valid message sequence but suddenly cut it from the middle. See how the state machine reacts to that, whether it leaves a session open or whether it might actually end up in a completely unexpected state. And try at all stages during the sequence. Again, try from the end until the first message. So when you are looking at sequences, you can try reordering things as well. So you can attack state machines simply by reordering the message sequence, make a valid message sequence, and try all kind of different permutations. Mangle it as you can. Or if you have a file format that has an expected order of structures, try to reorder them. Try to reorder the expected sequence of elements. Some special attacks. Version fields are very particular in many protocols and file formats. They are kind of like a key that opens up the remainder of the protocol, for instance. So a piece of software might blindly believe a version field in what kind of data will maybe come later in the protocol sequence or inside a particular message. So many times a version field is a very easy way to completely undermine the expectations of the software. Another thing is that when some protocol feature is, for instance, removed from a future version of the protocol, is it usually so that the implementations that are then ported to support the new specification are the parts really that pass the old protocol version, do they get removed or protected from usage? So usually what happens is that there's just added features, added ways to pass the new version of the protocol, but all of the old CRUD still remains within the software. All of the constructs that have been used to pass and process the old version of the protocol. And sometimes when a new version is released, testing is not that important anymore for the old version. So most testing concentrates on testing the next version, the newest version of the protocol, and it's really nobody really cares about the old version anymore. So you might find some locations in the code that have not been tested for 10 years maybe. Attacks against the version expectations is to try and claim to use a valid earlier version, but then use a completely different data within the message, or then try to use a completely unspecified version. Who knows what happens when you try to use like IP version 17 or something. Then another special attack case is the use of obsoleted or proprietary extensions. So there might be some specifications that have been forgotten about already. Some old internet drafts, for instance, from IETF, that have been discarded, that have been expired and nobody really implements anymore. But there might still be code for handling these kind of obsoleted features. And again, this code might be much less tested or even forgotten about completely. So there might be a module that passes particular obsoleted protocol specification, and nobody really even cares about testing it. The architecture for handling extensions is usually very general. There is things added over time to many implementations to handle new extensions. So over time it becomes a total mess because there are public extensions, proprietary extensions, obsoleted extensions, and extensions that you should be prepared for but which have not been specified yet. So any kind of code for handling extensions is very fruitful ground for basically doing anything. Even random fuzzing for extension fields is surprisingly effective. Also, if there are proprietary extensions, somebody might have done reverse engineering for these proprietary extensions, let's say competitors' extensions, and hacked together some kind of sort of like a mutant code that takes a look at these proprietary extensions and tries to make sense of them. So if somebody has not had full access to the specifications for these proprietary extensions, it's very likely that the code is just, it's a half-assed attempt at understanding the proprietary format. So you should always try to look for any obsoleted protocol features or file format features and try to break those things as well. Or try to emulate some version of the protocol that is obsoleted. Now, usually when we look at designing anomalous data, breaking the data from several locations is not typically that fruitful. And it's kind of a surprising thing. You would probably assume that when you fuzz multiple things at the same time, you are able to crash the software more effectively. But usually a single anomaly, a single input is enough to trigger one individual flaw. When you start adding the amount of fuzzed inputs into one single packet or one single file, you might miss some of the underlying problems. You might end up in a race condition, so to speak, where your fuzzing inputs, one of the fuzzing inputs triggers a particular flaw, but the other fuzzing inputs would never reach the flaws that would be out there. So I'm getting the red card now, so I'll have to skip a few things, but let's move a little bit forward. You can take a look at the data or the slides later on if there is some things. I want to stress a couple of more things. It's only going to take a minute or two. So when you are creating invalid inputs or malicious inputs, you should always try to be first as correct syntactically as possible. So if there are some checksums, message digests, different kind of signatures, for instance, mandated for a protocol, for instance, you should always make your attacks use these kind of mechanisms completely, and then only then start to undermine the underlying data structures. So try to be as valid as possible and then start tweaking the minute things that will then create or trigger the vulnerabilities. So if a protocol requires you to calculate a checksum, just do it. Make a model that does the checksum or the timing things that were discussed in the earlier wireless talk. So you should always try to be as valid as possible and then start creating attacks. Like I said, everything is TLV, and this is probably the most important thing to understand, is that you should always try to understand the next level substructures that you are trying to break. I have a couple of example attacks here at the end. I'll actually not go into this in that much detail. You can take a look at the links and the examples in more detail from the slides that will be up on the DeepSec website. I have an example of a length attack against a particular Bluetooth implementation. So I was hoping that maybe Marcel could talk about this at some point. Underflow attack. One example from a zip implementation and a naive way to protect against this attack. Implicit value from X509. This is the famous parasitic keys attack, where simply choosing particular values for public keys for the public exponent and public modulus values caused degradation of service in many implementations. Again, things with implicit values combined with usage of obsoleted protocol feature. Repetition, again, combined with an implicit value expectation. These kind of things. State machine mangling. So this particular attack looked at sending a very advanced broken sequence of zip requests and then caused a problem in a particular zip implementation. So I'd like to, in the end, I'd like to thank my colleagues from Codenomicon for some of their research around this area. And then we don't have any time for questions, but I'm sure we can have one question if somebody really feels the need to ask. Or you can come and discuss with me later on, or in the cocktail event in the evening. Any questions? Okay, go ahead. Yeah, so my company, we make fuzzers for various protocols and file formats. We have a fuzzing framework that we use to create the fuzz tests. But this is not a product pitch, so go to the website if you want more on that. But yeah, we have a fuzzing framework for doing this, as do many others nowadays. Okay, thank you.